In January 2026, a group of scientists from the University of Chicago, MIT, and Stanford published a paper in the journal Science that made an extraordinary claim. They said quantum computing has reached its transistor moment.
Okay, transistor moment. That sounds huge, but what does that actually mean?
Think about what the transistor did. Before it, computers were the size of rooms. They used vacuum tubes that burned out constantly. The transistor was this tiny, reliable switch that changed everything. It led to the microchip, personal computers, smartphones, the entire digital world. Every piece of technology you touch exists because of that one invention.
And they're saying quantum computing is at that same inflection point right now.
That's exactly what they're saying. The foundational physics is proven. Working systems exist. Multiple companies have functional quantum processors you can access through the cloud right now. What's missing is the same thing that was missing for transistors in the late 1940s: scale, reliability, manufacturing, the engineering to turn a lab breakthrough into something that reshapes civilization.
So we're not waiting for some magical discovery anymore. It's more like an engineering challenge at this point.
Right? And here's what makes this moment different from 5 years ago. 5 years ago, the big question was whether quantum error correction could actually work in practice, because quantum computers have this fundamental problem. The qubits, the quantum bits that store information, are incredibly fragile. They lose their quantum state in microseconds. Every operation introduces tiny errors, and for decades, the more qubits you added, the more errors you got. It seemed like an impossible scaling problem.
That does sound like a deal breaker. How do you build a useful computer if it gets worse as it gets bigger?
That was the trillion-dollar question, and in the last 2 years, four separate teams independently proved it's solvable. Google's Willow chip was the first bombshell. In late 2024, they demonstrated something physicists had been chasing for 30 years. They scaled up from a 3 by 3 grid of qubits to a 5 by 5 to a 7 by 7, and at each step the error rate went down, not up. They cut errors in half with each increase in size.
Wait, so bigger actually means more accurate? That completely flips the old problem.
Completely flips it. And Google wasn't alone. Quantinuum, working with Microsoft, created logical qubits with error rates 800 times lower than the physical qubits underneath them. Then Microsoft published new four-dimensional geometric codes that achieved a thousand-fold error reduction, and then a team at the University of Science and Technology of China in Hefei replicated similar results with their own approach.
Four different teams, four different methods, all converging on the same conclusion. That's not a fluke.
Not even close. And this is why the Nature article from last week used the phrase vibe shift. That's a quote from Natalie De Leon, a quantum physicist at Princeton. She said that's what's happening in the field right now. People who thought useful quantum computers were decades away are revising their timelines. Dorit Aharonov, a computer scientist at Hebrew University, who literally helped develop the theory of quantum error correction, said she now believes the timeline is much shorter than anyone thought.
Okay, so the error problem is getting solved, but I still don't really understand what a quantum computer can do that a regular computer cannot. Like, what's the actual payoff?
This is the part that gets wild. A classical computer processes information as bits, zeros and ones. A quantum computer uses qubits, which can exist as 0, 1, or a superposition of both simultaneously, but the real power isn't superposition, it's entanglement. When qubits are entangled, the information they can jointly represent grows exponentially with each qubit you add.
Exponentially. Like, 2 qubits doesn't mean twice as much, it means 4 times as much.
That's right. 10 qubits can represent 1024 states simultaneously. 50 qubits can represent over a quadrillion states. 300 entangled qubits can represent more states than there are atoms in the observable universe.
That's an insane amount of computing power. So, why aren't we using it for everything?
Because you can only extract the answer through measurement, which collapses all those possibilities into a single result. You need cleverly designed algorithms that funnel the computation toward the right answer before you measure, and those algorithms only give quantum computers an advantage for specific types of problems.
What kind of problems?
Drug discovery is the big one. Simulating how molecules interact at the quantum level is essentially impossible for classical computers once you go beyond simple molecules. A classical computer would need more memory than exists on Earth to simulate a medium complexity protein. A quantum computer could potentially do it in hours. That means designing new drugs, new materials, new catalysts, all from simulation instead of decades of trial and error.
What else?
Cryptography. Most internet encryption relies on the fact that factoring enormous numbers is practically impossible for classical computers. A sufficiently powerful quantum computer could break RSA encryption in minutes using Shor's algorithm. That's why governments worldwide are already switching to post-quantum cryptography standards.
That sounds terrifying and amazing at the same time.
It gets better. Financial modeling, logistics optimization, climate simulation, machine learning. Google demonstrated that Willow could solve a specific computation in under 5 minutes that would take the fastest classical supercomputer 10 septillion years. That's 10 to the power of 25 years. The universe is only about 13.8 billion years old.
10 septillion years. I cannot even process that number.
Nobody can. And yes, that was a carefully chosen benchmark problem. Real world useful quantum advantage is still coming, but the point is that the raw computational power is real. It's not theoretical anymore.
So, who's actually building these things? Is it just Google?
It's a massive global race. Google, IBM, Microsoft, Amazon all have major quantum programs. IBM has been shipping quantum processors through the cloud since 2016 and released their first 1,000-qubit chip in 2023. Amazon unveiled Ocelot, their first proprietary quantum chip, built with cat qubits that naturally suppress errors.
Cat qubits, like Schrodinger's cat.
Kind of cat qubits encode information in a way that's inherently resistant to certain types of errors, like having a self-correcting mechanism built into the hardware itself. Then you've got startups. Quantinuum is doing trapped ion quantum computing with the highest fidelity gates in the industry. PsiQuantum raised over $600 million to build a million-qubit photonic quantum computer. Quera, a Harvard spin-off, is using neutral atoms trapped by laser beams. Each approach has different strengths.
And they're all taking different paths to the same goal.
That's right. The science paper reviewed 6 major hardware platforms. Superconducting qubits like Google and IBM use are currently the most advanced for raw computing. Trapped ions from Quantinuum lead in gate fidelity. Neutral atoms from Quera and others are winning in quantum simulation. Photonic qubits are best for quantum networking. Each platform has its own scaling challenges.
It's like the early days of computing when you had mainframes, minis, and micros all competing.
Perfect analogy, and just like then, the winner might not be one single approach. We might end up with hybrid systems that combine different qubit types for different tasks.
How many qubits do we actually need for the big applications, like drug discovery or breaking encryption?
Current estimates say useful quantum chemistry might need 1 million physical qubits with very low error rates. Breaking RSA 2048 encryption would need around 4 million physical qubits. The biggest machines today have around 1,000 physical qubits, so there's still a gap. But here's the key insight from the error correction breakthroughs. You don't necessarily need 1 million perfect qubits. You need enough physical qubits to create a smaller number of logical qubits through error correction. And the better your error correction gets, the fewer physical qubits you need per logical qubit.
So the error correction advances are essentially a shortcut to useful machines.
Huge shortcut. Microsoft's new 4-dimensional codes need far fewer physical qubits per logical qubit than previous methods. That could compress the timeline dramatically.
What's the realistic timeline then? When does this actually affect regular people?
The science paper's authors estimate we're in the equivalent of the late 1940s to early 1950s of classical computing. Functional systems exist, but scaling and manufacturing are the bottleneck. Their best guess for practically useful quantum computers is within the next decade, so somewhere around 2030 to 2035 for the first genuinely transformative applications.
That's incredibly soon. A decade ago, people were saying 50 years.
The error correction breakthroughs compress the timeline by decades, and there's a market signal too. McKinsey estimates quantum computing could be $1 trillion market. Over $40 billion of venture capital has flowed into quantum startups. Equal One just raised $60 million to build quantum computers using existing semiconductor manufacturing processes. That last part is crucial. If you can build quantum chips in existing chip fabs, you can scale production massively.
Using existing chip factories? That would be a game changer.
It would bypass the biggest bottleneck right now. Quantum chips need specialized fabrication. If you can use standard CMOS processes, the ones that make every chip in your phone and laptop, you inherit decades of manufacturing optimization overnight.
I keep thinking about the transistor comparison. The transistor was invented in 1947. The first integrated circuit was 1958. The first microprocessor was 1971. The iPhone was 2007. That's 60 years from transistor to smartphone.
And the pace of technological change has accelerated enormously since then. We have AI, we have advanced manufacturing, we have global collaboration that didn't exist in the 1950s. The quantum computing timeline from here to transformative applications could be dramatically compressed.
So we're living through the equivalent of 1947 for quantum computing, the moment right before everything changes.
That's exactly what those scientists are telling us. The physics works, the engineering is catching up, the money is flowing, the timeline just got a lot shorter. We're watching the birth of a technology that will reshape computing, medicine, materials, science, cryptography, and probably things we haven't even imagined yet.
And most people have no idea this is happening right now.
That's the thing about transformative moments. When the transistor was invented, almost nobody noticed. It was just a tiny piece of germanium in a lab at Bell Labs in New Jersey. No headlines, no fanfare. It took years before anyone realized it would change the world. We might be at that same quiet moment right now, except this time you heard about it first.
And now we're all watching. This is going to be fascinating to follow.
It really is. And if you want to keep watching it unfold with us, make sure you're subscribed, because this story is just getting started.